In computer science, a for loop is a programming language statement which allows code to be repeatedly executed. A for loop is classified as an iteration statement. The key word used to declare a for loop is based on the heritage of the language and the prior programming languages it borrowed from, so programming languages that are descendants of or offshoots of a language that originally developed an iterator will often use the same key word to name an iterator. For example, descendants of ALGOL will use for, while descendants of Fortran will use do. Some languages started from scratch, and didn't have a predefined term for an iterator to choose from, which is why COBOL uses perform varying. Unlike many other kinds of loops, such as the while loop, the for loop is often distinguished by an explicit loop counter or loop variable. This allows the body of the for loop to know about the sequencing of each iteration. For loops are also typically used when the amount of iterations is known before entering the loop. For loops are the shorthand way to make loops when the number of iterations is known, as a for loop can be written as a while loop. The name for loop comes from the English word for, which is used as the key word in most programming languages to introduce a for loop. The term in English dates to ALGOL 58 and was popularized in the influential later ALGOL 60. It is the direct translation of the earlier German Far 1/4 used in Supraplan by Heinz Rütishauser, who also was involved in defining ALGOL 58 and ALGOL 60. The loop body is executed for the given values of the loop variable, though this is more explicit in the ALGOL version of the statement, in which a list of possible values and/or increments can be specified. In Fortran and PLI though, the keyword do is used and it is called a do loop, but it is otherwise identical to the for loop described here and is not to be confused with the do while loop. Kinds of for loops. A for loop statement is available in most imperative programming languages. Even ignoring minor differences in syntax, there are many differences in how these statements work and the level of expressiveness they support. Generally, for loops fall into one of the following categories: traditional for loops. The traditional for loop found in C++ requires three parts: the initialization, the condition, and the afterthought. The initialization declares any variables required. The condition checks a condition, and quits the loop if false. The afterthought is performed exactly once every time the loop ends and then repeats. Here is an example of the traditional for loop in Java 7. Iterator-based for loops. This type of for loop is a falsification of the numeric range type of for loop, as it allows for the enumeration of sets of items other than number sequences. It is usually characterized by the use of an implicit or explicit iterator, in which the loop variable takes on each of the values in a sequence or other orderable data collection. A representative example in Python is where some iterable object is either a data collection that supports implicit iteration, or may in fact be an iterator itself. Some languages have this in addition to another for loop syntax. Notably, PHP has this type of loop under the name for each, as well as a three-expression for loop under the name for. Vectorized for loops. Some languages offer a for loop that acts as if processing all iterations in parallel, such as the for all keyword in Fortran 95, which has the interpretation that all right-hand side expressions are evaluated before any assignments are made, as distinct from the explicit iteration form. For example, in the for loop in the following pseudocode fragment, when calculating the new value for a, I, except for the first, the reference to a, I, 1, will obtain the new value that had been placed there in the previous step. In the for all version, however, each calculation refers only to the original, unaltered a. For I, equals to, n, 1 do a, I, equals, a, I, 1, plus a, I, plus a, I plus 1, /3. Next I. For all I, equals to, n, 1 do a, I, equals, a, I, 1, plus a, I, plus a, I plus 1, /3. The difference may be significant. Some languages also offer array assignment statements that enable many for loops to be omitted. Thus pseudocodes such as a equals 0 would set all elements of array A to 0, no matter its size or dimensionality. The example loop could be rendered as. But whether that would be rendered in the style of the for loop or the for all loop or something else may not be clearly described in the compiler manual. Compound for loops, introduced with ALGOL 68 and followed by PLI, this allows the iteration of a loop to be compounded with a test, as in for I equals 1, n while I, 0 do etc. That is, a value is assigned to the loop variable I and only if the while expression is true will the loop body be executed. If the result were false the for loop's execution stops short. Granted that the loop variable's value is defined after the termination of the loop, then the above statement will find the first non-positive element in array A, or, with suitable variations, the first non-blank character in a string, and so on. Additional semantics and constructs, uses infinite loops. This C-style for loop is commonly the source of an infinite loop since the fundamental steps of iteration are completely in the control of the programmer. In fact, when infinite loops are intended, this type of for loop can be used, such as this style is used instead of infinite while, 1, loops to avoid a warning in Visual C++. Early exit and continuation. Some languages may also provide other supporting statements, which when present can alter how the for loop iteration proceeds. Common among these are the break and continue statements found in C and its derivatives. The break statement causes the innermost loop to be terminated immediately when executed. The continue statement will move at once to the next iteration without further progress through the loop body for the current iteration. Other languages may have similar statements or otherwise provide means to alter the for loop progress. For example in Fortran 95. Loop variable scope and semantics, different languages specify different rules for what value the loop variable will hold on termination of its loop, and indeed some hold that it becomes undefined. This permits a compiler to generate code that leaves any value in the loop variable, or perhaps even leaves it unchanged because the loop value was held in a register and never stored to memory. Actual behavior may even vary according to the compiler's optimization settings, as with the ALGOL Fortran 66 compiler. In some languages the loop variable is immutable within the scope of the loop body, with any attempt to modify its value being regarded as a semantic error. Such modifications are sometimes a consequence of a programmer error, which can be very difficult to identify once made. However, only overt changes are likely to be detected by the compiler. Situations where the address of the loop variable is passed as an argument to a subroutine make it very difficult to check, because the routine's behavior is in general unknowable to the compiler. Some examples in the style of Fortran. A common approach is to calculate the iteration count at the start of a loop and with each iteration decrement this count while also adjusting the value of I, double counting results. However, adjustments to the value of I within the loop will not change the number of iterations executed. Still another possibility is that the code generated may employ an auxiliary variable as the loop variable, possibly held in a machine register, whose value may or may not be copied to I on each iteration. Again, modifications of I would not affect the control of the loop, but now a disjunction is possible. Within the loop, references to the value of I might be to the current value of I or to the auxiliary variable and confusing results are guaranteed. For instance, within the loop a reference to element I of an array would likely employ the auxiliary variable, but if I is a parameter to some routine, it would likely be a reference to the proper variable I instead. It is best to avoid such possibilities. List of value ranges, PLI and ALGOL 68, allows loops in which the loop variable is iterated over a list of ranges of values instead of a single range. The following PLI example will execute the loop with 6 values of I, 1, 7, 12, 13, 14, 15. Equivalence with while loops. A for loop can be converted into an equivalent while loop by incrementing a counter variable directly. The following pseudocode illustrates this technique. Factorial equals 1, for counter from 1 to 5, factorial equals factorial counter. Is easily translated into the following while loop. Factorial equals 1, counter equals 1, while counter less than or equal to 5, factorial equals factorial counter, counter equals counter plus 1. This translation is slightly complicated by languages which allow a statement to jump to the next iteration of the loop. These statements will typically implicitly increment the counter of a for loop, but not the equivalent while loop. Any translation will have to place all such statements within a block that increments the explicit counter before running the statement. Syntax: given an action that must be repeated, for instance, 5 times, different languages for loops will be written differently. The syntax for a 3-expression for loop is nearly identical in all languages that have it, after accounting for different styles of block termination and so on. Action script 3. Ada. The exit statement may be used to exit the loop. Loops can be labeled, and exit may leave a specific labeled loop in a group of nested loops. Apple script. You can also iterate through a list of items, similar to what you can do with arrays in other languages. You may also use exit repeat to exit a loop at any time. Unlike other languages, Apple's script does not currently have any command to continue to the next iteration of the loop. Bash. Note that an empty loop is a syntax error. If the above loops contained only comments, execution would result in the message syntax error near unexpected token done. Basic. Notice that the end loop marker specifies the name of the index variable, which must correspond to the name of the index variable in the start of the for loop. Some languages allow a statement label on the start of a for loop that can be matched by the compiler against the same text on the corresponding end loop statement. Fortran also allows the exit and cycle statements to name this text. In a nest of loops, this makes clear which loop is intended. However, in these languages the labels must be unique, so successive loops involving the same index variable cannot use the same text, nor can a label be the same as the name of a variable, such as the index variable for the loop. See C++. The statement is often a block statement. An example of this would be the ISO IEC 9899/1999 publication also allows initial declarations in for loops. CFML, script syntax, simple index loop. Using an array. Using a list of string values. The above list example is only available in Relo's dialect of CFML. Tag syntax, simple index loop. Using an array. Using a list of string values. Fortran, while using the keyword do instead of for, this type of Fortran do loop behaves similarly to the 3-argument for loop in other languages. This example behaves the same as the others, initializing the counter variable to 1, incrementing by 1 each iteration of the loop and stopping at 5. Haskell, the built-in imperative form maps a monadic expression into a list, as or get each iteration result as a list in. But, if you want to save the space of the 1-5 list, a more authentic monadic for loop construction can be defined as and used as. Java. For the extended for loop, see for each loop, JavaScript. JavaScript supports C-style 3-expression loops. The break and continue statements are supported inside loops. Alternatively, it is possible to iterate over all keys of an array. So, this code will print. For loops can also loop through a table using to iterate numerically through arrays and to iterate randomly through dictionaries. Generic for loop making use of closures. Mathematica, the construct corresponding to most other languages for loop is called do in Mathematica. Mathematica also has a for construct that mimics the for loop of C-like languages. MATLAB. Maxima CAS, in Maxima CAS one can use also non-integer value ISA. Oberon 2, Oberon 07, or component Pascal. Note that in the original Oberon language the for loop was omitted in favor of the more general Oberon loop construct. The for loop was reintroduced in Oberon 2. OCaml, see expression syntax. Pascal. Decrementing is using down to keyword instead of to, as in. The numeric range for loop varies somewhat more. Perl. Note that there's more than one way to do it as a Perl programming motto. PHP. PLI. The leave statement may be used to exit the loop. Loops can be labeled, and leaf may leave a specific labeled loop in a group of nested loops. Some place-I dialects include the iterate statement to terminate the current loop iteration and begin the next. Postscript. Postscript supports a very simple kind of for loop. The repeat loop, written as x. Repeat, repeats the body exactly x times. Python. Ruby. Ruby has several possible syntaxes, including the above samples. Smalltalk. Contrary to other languages, in Smalltalk a for loop is not a language construct but defined in the class number as a method with two parameters, the end value and a closure, using self as start value. Timeline of the for loop in various programming languages, 1957, Fortran. Fortran's equivalent of the for loop is the do loop. The syntax of Fortran's do loop is where the step part may be omitted if the step is 1. Example. 1958, ALGOL. ALGOL was first formalized in the ALGOL 58 report. 1960, COBOL. COBOL was formalized in late 1959 and has had many elaborations. It uses the perform verb which has many options, with the later addition of structured statements such as end perform. Ignoring the need for declaring and initializing variables, the equivalent of a for loop would be if the perform verb has the optional clause test after, the resulting loop is slightly different, the loop body is executed at least once, before any test. 1968, ALGOL 68. ALGOL 68 has what was considered the universal loop, the full syntaxes. Further, the single iteration range could be replaced by a list of such ranges. There are several unusual aspects of the construct. Only the do-odd portion was compulsory, in which case the loop will iterate indefinitely. Thus the clause to 100 do-odd, will iterate exactly 100 times. The while syntactic element allowed a programmer to break from a for loop early, as in subsequent extensions to the standard ALGOL 68 allowed the syntactic element to be replaced with up-to and down-to achieve a small optimization. The same compilers also incorporated until for late loop termination, for each, for working on arrays in parallel. 1983, ADA 83 and above. Implementation in interpreted programming languages. In interpreted programming languages, for loops can be implemented in many ways. Oftentimes, the for loops are directly translated to assembly-like compare instructions and conditional jump instructions. However, this is not always so. In some interpreted programming languages, for loops are simply translated to while loops. For instance, take the following Mint-Hort charter code. See also, do while loop, for each, loop counter, while loop, references. External links, for loop implementation in different languages at Wikia, code.